Welcome to MyProjectBazaar.com. Let me discuss about the process optimal cooperation strategy in cognitive radio systems with energy harvesting. Let me discuss about the abstract of the project. Energy harvesting is a highly promising technology which can support continuous power supply to energy constrained communication systems such as machine to machine and sensor networks. Usually the main goal of the EH communication system is to maximize the system throughput under some causality constraints. The harvested energy can originate from the far field radio frequency radiation of another device, a closely located communication transmitter which can transfer power and information simultaneously, or from the ambient RF radiation. If an energy constrained system does not have dedicated communication resources, it can still be implemented as a secondary user system in a cognitive radio setup. The CR system utilizes one of the following three methods for spectrum sharing: interview, underlay, and overlay spectrum sharing. In the interview approach, the CR devices perform spectrum sensing to detect the unoccupied incumbent bands and then access the channel in this band. In the underlay approach, CR devices operate in the same band as the primary users and are allowed to interfere with the primary system under some predefined threshold. In this system, PU and SU is located where both are requested for accessing the channel. PU uses licensed channel, whereas SU uses unlicensed channel for transmitting the data. SU harvesting energy from ambient temperature, while PU transmitted data via channel. SU starts to transmit the data when PU turns to silence. There are two approaches proposed, that is non-cooperation mode and cooperation mode. Evaluate the performance by analyzing such as optimal save ratio, optimal relay power, and achievable throughput. Let me discuss about the flow diagram for our process. Initially, the system model has been designed. Cooperative communication between PU and SU is considered as the SU's option to potentially increase the PU's throughput, such that the licensed channel could be vacated and more transmission opportunities could be provided for the SU. In order to do so, the SU must consume its harvest energy to help relay the PU's data. This cooperation can take place in several ways, depending on the cooperation protocol being used. In this paper, we assume the cooperative communication between PU and SU follows the decode and forward protocol, which is one of the commonly used protocols. In the DF protocol, the relays first decode and the received signal, re-encode it, and then transmit it to the destination. Finally, the destination uses both the signals jointly to decode the data. In non-cooperative mode, the system focuses on that is optimization for the SU's achievable throughput in each time slot. We assume that the SU must exhaust all the harvested energy in each time slot for data transmission, because it is meaningless to penny pinch harvested energy, which means the SU's energy storage is emptied at the beginning of each time slot. The SU's activities are powered exclusively by energy harvested from ambient signal. Following the harvested energy from the transmit protocol, the SU devotes the fraction of time to energy harvesting in each time slot. In time slotted operation mode, the more time spent on energy harvesting, more energy can be harvested, which leads to higher SU's instantaneous transmission rate, whereas less time remains. In cooperation mode, a time slot is partitioned into three fractions synchronous for both PU and SU. While operating in cooperation mode, the decode how much its harvested energy is allocated to help relay the PU's data as well, evidently with more energy consumed for cooperative mode. PU's transmission could be completed earlier such that the more opportunities could be available for secondary transmission, whereas less energy is reserved, which inevitably limits the SU's achievable throughput. Finally, the optimal decision has been taken. For the non-cooperative mode, the optimal save ratio can be easily derived according to ninth equation for the cooperation mode. The optimal solution can be derived by comparing the optimal achievable throughput for the two KKT candidate points. Finally, the optimal decision can be made by comparing the optimal achievable rate in the two modes. Finally, the performance graph has been analyzed. Since the proposed OCP is based on the closed form solution to the achievable throughput maximization problem, optimal cooperation strategy can be readily derived. Let me discuss about the running procedure for our process. Select the main dot template, the control right in the middle and run for executing this process. Here, optimal cooperation strategy for our primary and secondary usage. This is the optimal save ratio by varying the received signal, and this is also optimal save ratio by varying the number of users. Here gamma s values also vary. Here the optimal relay power, that is consumption of power by for our various users rate. This is the optimal relay power for our RP different RP values, and this is the achievable throughput ratio. In the case of x equal to 10, 5, that is primary user is 10 and secondary user is 5, and gamma s values will be the range of 1 by 500, and this is the achievable throughput for our x equal to 20, 5, and gamma s is 1 by 1000. Here this is the achievable rate by varying the time slot. Here the x equal to 10, 5 and gamma is equal to 1 by 1000. This is also achievable throughput graph by varying the different time slot. Here x equal to 30, 5 and gamma is equal to 1 by 1500. This is the achievable throughput by varying the various time slot. X equal to 20, 5. This is the bar graph for our average achievable throughput for our OCP protocol. Finally, we obtain the optimal cooperation protocol for both primary user and secondary user. Thank you.